And so we'll first talk about discrete time signals and this fundamental block diagram where we have some continuous time signal, x of t. We digitize the signal with an A to D converter to produce a sequence x of n. And finally, in the simplest of digital signal processing systems, we have a digital to analog converter to produce an output y of t. And so we're just assume the same clock for the A to D and D to A converter. And we'll have a clock period t0. And so we have a continuous time input. And after we digitize it, we see the familiar stepwise version at the output of this simplest system, perhaps simplest mixed analog and digital system. Finally, our definition of x of n is it's the continuous time system evaluated at multiples of the clock period t0. And so it's the continuous time signal in our notation will be some function with parentheses or rounded brackets indicating continuous time variable, and the square brackets indicating discrete time, where the argument is an integer n. So again, in most systems, our continuous time signal is the starting point that is digitized to produce our discrete time sequence x of n. And so here we have the samples plotted as a function of index n. So we have x of 0, x of 1, and x of 2, and so forth. And so there may be some continuous time function that is sampled using the sampler with a sampling period t0. And so just as a quick illustration, consider a sampled sinusoid. So where the sampling period again is t0. And so our x of n is the continuous time function sampled at n times t0, replacing t. And so if we have a carrier, continuous time carrier frequency, omega c, again, we'll use the capital omega for continuous time frequencies. And we'll see in a moment that the lowercase omega is for discrete time frequencies. And so we'll follow that convention throughout the course. And so omega c is the carrier frequency of the sinusoid. And so our x of n, we replace the t by nt0. Here we've also replaced omega c. So omega c equals 2 pi over the period of the sinusoid, the continuous time sinusoid, so the carrier frequency period t sub c. And so we can factor the n out, and so we have omega c times t0 times n. And so this is our definition now of the discrete time frequency. Discrete time frequency, again, the lowercase, so the carrier frequency of the sinusoid, omega c, which is the continuous time frequency times the period of the sampler. And so here we have the definitions. Carriers, 2 pi over the period in seconds. We could also say the carrier frequency in hertz is 1 over the period of the carrier. The sampling frequency, which would be 1 over t0 in hertz, can also be expressed in units of radians per second. So the continuous time frequency, again, is just omega c times t0. And we can write this a number of different ways, either as a ratio of the continuous time frequency to the sampling frequency, or as just omega c t0 as we saw above, or as a ratio of the carrier frequency in hertz divided by the sampling frequency in hertz, or as the ratio of the sampling period t0 divided by the period of the sinusoid. And so we can just substitute variables, see a number of ways define the discrete time frequency. So here we have a sketch of a sinusoid, and here, remember, T sub c was the carrier period, and so we see that this sinusoid has a 2-second period. Our sample period is half a second, and so we have samples at 0, half, 1, 1.5, and 2. And so from those samples, we can see that we have the sample values. Here we started at 0, 1, 0, -1, so forth, repeating. The discrete time frequency, again, we can derive for a number of ways. I think the initial method, so let's double check this. First of all, what is omega c? Well, it's 2 pi over the carrier frequency, the carrier period, which is 2 seconds. And so omega c must be pi. And if you recall, omega c equals omega c times t0, and that equals now pi times 1/2. So it's pi over 2. We can use any of the other forms also to show that the frequency is pi over 2. What's important here to see is that the units of the discrete time frequency is radians per sample. One way to see that is from conservation of units. Remember, omega equals omega times t0. And if we look at the units on this, we have radians per second times seconds per sample, because the period is how many seconds long a sample period is. And so we could just cancel the units and we get radians per sample. Another way to see this is if you look at these sample points in the sinusoid, how many radians does the sine wave go between 0 and 1? And of course, that's pi over 2 radians. When you go to pi radians, sine comes back to 0, so it moved another pi over 2. And so it has a physical meaning. And so it is indeed the radians per sample of a sinusoid. This brief introduction to the most simple system with an A to D and D to A converter is also useful to kind of review what is the mathematical model of this simple system. And so here below we have a simple model, and we'll see that it produces the same input and output. And so here we have the continuous time signal at the input. We multiply it by an impulse train where the period of the impulse train is t0, so it's running at the sample rate. This is, of course, called delta t0 of t, which is this infinite sum of delayed impulses. This multiplied together produces the sampled signal excess of t. And here we've just shown the multiplication and indicated that the weights of each of these impulses is proportional to the original continuous time signal. Of course, they're infinitely high, but the area is set by the weight, which is indicated by the drawing of the height of the arrows. But remember, it's the area that's established, not the height is infinite in all cases. Finally, to produce the output that's the same as we had the A to D, D to A pair, we put it through a filter whose response is a pulse of width t0 starting at 0 and of height 1. And so by definition, if you put an impulse into this filter, out comes h of t, which is this rectangular pulse. And so if I put an impulse in twice as high, twice the weight, then an output would come another pulse of height 2. If I put a pulse in later in time, I would get a pulse out later in time. So this basic principle means that at each of these locations, I get a pulse whose amplitude is proportional to the weight of the delta function, which is finally gives us this last input, the stepwise output that looks like the digital approximation to the original input. And so the important thing here is that this system basically replicates, somehow this mathematical model incorporates the basic principles of the most simple digitization circuit, simple A to D followed by D to A. By the way, the function h of t, the pulse is just a rectangular pulse of width t0 and shifted by t0 over 2. Again, reminding that this pi or gate function is a rectangular pulse function centered at 0 with tau. And so the definition of h of t comes from that. And so at each step in this block diagram, we can take a look at the Fourier transform of the corresponding signal. And so for x of t, again, that's our continuous time signal. Its Fourier transform, just to draw it easily, will be a triangular spectrum with a peak value a centered at frequency 0. Again, this is in radians per second. This is continuous time frequency. And so again, we have the impulse train, the Fourier transform of the impulse train, which is our input at the bottom of the multiplier. Its Fourier transform is an impulse train at frequency. The weights of all these delta functions are 2 pi over t0, and they occur at multiples of the sampling frequency. So 2 omega 0, omega 0, minus omega 0, and so forth. Well, these two are multiplied together, these two functions up top in time. So in frequency domain, that multiplication becomes a convolution. And so the easiest convolution, so if we recall, if I have a box with an impulse response h of t, its output is the convolution of h of t with the input, but if the input is just an impulse, a delta function, then the output is just h of t. So if I delay that input, of course, the output is delayed. And if I double the input, the output is doubled. And so by this argument, this convolution that we need to do in the frequency domain is very easy to do. I just take and replace each one of these impulses by the corresponding second function, which is the triangle. And so we see that below at the location of each impulse, I have a triangle which represents the original spectrum, and it's multiplied 2 pi over t0 times a. However, when you multiply two things in time, the Fourier transform is not the convolution, but it's 1 over 2 pi times the convolution. So I have a factor of 2 pi that disappears, so what I'm left with is a over t0. And so the output spectrum is the Fourier transform of the multiplied together this continuous function times the impulse train. Its Fourier transform of x of s is xs of omega, which is this periodic repetition of the original spectrum divided by t0. Remember, t0 is the sample period. So the next stage is our rectangular pulse, h of t, right, is the response. And so the Fourier transform h of t is a sinc function. It has a sinc type magnitude with peak t0, crosses through 0 multiples of omega 0. It does have a phase shift since it's not centered at 0, and so we plot the magnitude of it here. Finally, the output y of t is the convolution of xs with h of t. However, that convolution in time is multiplication of the frequency spectra. And so I just need to multiply xs of omega by h of omega to find the final spectrum. We'll say one thing. Notice that this sinc function is relatively flat near zero, and so I've redrawn the spectrum in that vicinity when I multiply these two together to be approximately the same shape. The t0 peak of the sinc function cancels out the t0 in the denominator, and so I end up with a peak A. So this central spectrum looks a lot like the original spectrum above. I get small components at multiples at the multiples of the spectrum because it's multiplying a small value of the sinc function in each of these vicinities multiplies the corresponding spectra above it. And so we can think of these remnants of the spectrum as the pieces that contribute to the stepwise version of the original signal. And again, the original signal just had the nice clean spectrum with one triangle centered at zero. And so we've used the Fourier transform of each of those different signals to get insight as to what's happening in the frequency domain. So we can redraw this mathematical model at each point. So now I have the spectrum of the input signal. I have the spectrum of the impulse train that multiplies that signal. I have the spectrum at the output now that's periodically replicated. And so the output consists of multiples of the spectrum divided by t0. And finally, going through this last stage, the output spectrum, again, this is called a zero order hold, this particular filter response. The output now is this spectrum. It looks a lot like the original spectrum at the output, near zero, but has these extra remnants which we can be thought of as the components of the spectrum that produce the stepwise version. Just as quick review, of course, the Fourier transform in our case, we used a capital omega as our continuous time variable, and so it follows the normal definition of a Fourier transform. Similarly, the inverse transform, but using capital omega for our continuous time frequency variable. So one of the important conclusions or uses of this frequency domain view of things is that the spectrum of that sampled spectrum, if I start with the original spectrum where the triangular spectra are separated quite well, if I lower the sample frequency, this triangle starts to move lower until the point where they just touch each other. And so we've illustrated that here, where the frequency where the two spectra touch. So this is the first replica, this is the original spectrum, is at the highest frequency component of the frequency spectrum. And so 2 pi b would be the frequency in radians per second, so b would be the highest frequency in hertz. If I lower this frequency of the sample rate any lower, what I see is that the spectrum overlap is shown here. And when they overlap, I lose information. So what actually happens is I don't see this overlapping lines drawn. I get the values to add together. And so, for example, if the value was 4 here, there would be no way for me to tell whether that was because a 1 plus 3 produced a 4 or a 2 plus 2. So I lose the information in those spectra because they get added together. And this is a frequency domain explanation of aliasing. And so you need to, so the minimum sample rate to prevent aliasing is the Nyquist rate 2b, where b is the bandwidth of the signal or the highest frequency in the signal. So b was, of course, that point. 2 pi b was the point in radians per second, which corresponded to the highest frequency of the original spectrum. So the sample rate must be greater than 2 times that highest frequency. And again, the sample rate is 1 over the sampling period t0 that we had mentioned before. So this sampled signal excess of t and its Fourier transform um, lead us to what's called the discrete time Fourier transform. And so if we take a look at the Fourier transform of excess of t, so that would be excess of capital omega. Again, this is our continuous time variable. It's excess of t e to the minus j omega t, just using the definition of Fourier transform. Recall that this sampled signal is just the values at each time point times a delta function at that time point. So we can substitute in for excess of t. And then we'll interchange the order of summation and integration, bring the sums out front. And notice that I have an integral for a transform of a delayed impulse. Well, each one of those equals e to the minus j omega nt0. And so I have now a expression for the Fourier transform of that sampled function. Remember this sampled function out here. If I had my continuous time signal here, was the function that consisted of those weighted delta functions, which may represent the sample values in the mathematical model. And so this was excess of t, which is the impulse train times x of t. Well, from that, we'll just propose the definition of what's called the discrete time Fourier transform. So here, notice that we're using our discrete time variable. So this units would be radians per sample. And now we're defining a discrete time or digital Fourier transform. So the discrete time Fourier transform. So we, in the definition, we just have the sample values x of n, and now times e to the minus j omega n, where omega is, of course, our discrete time frequency variable. The inverse transform is 1 over 2 pi. This is a continuous integral now for the inverse transform. It looks like a normal Fourier transform, except now our variables are the discrete time Fourier transforms in radians per sample instead of radians per second. One last thing, this is not minus infinity infinity for the inverse transform. Be careful, it's minus pi to pi. Typically, inverse transforms are done using lookup table of a Fourier transform table. But what I like to do is compare this to the result of excess omega, the Fourier transform of that sampled signal. And again, this is the continuous time, so this is the transform of those weighted impulse version of the original sampled signal. And so that Fourier transform, by comparison, looks the same. These x of nt0s, by definition, equal the x of n's. And so the only real difference that we have between the two is I have omega times t0 here, where I have lowercase omega. Of course, that's our definition that we had before for relating the discrete time frequency, lowercase omega, to the continuous time frequency, capital Omega. So now we see that this definition of discrete time Fourier transform is the same as the spectrum of that sampled signal, just by changing the variable capital Omega and replacing it by omega over t0. That's just a simple rearrangement of this. Before we go, some textbooks, when you use Z-transform and Fourier transforms, use x of e to the j omega. There's a reason to do that, but I think it can sometimes be confusing. So in my notation, I use x of omega. If you have some other reference books that use x of e to the j omega, it would be the check to see that it's the same notation that I'm just using x of omega instead. So this makes it very straightforward to extend our earlier results to the discrete time Fourier transform now. And we can see a few things. The discrete time Fourier transform frequency variable. Omega is a continuous variable, just like omega is in the continuous time Fourier transform. It's periodic in omega, so it turns out it has a period of 2 pi. And so recall that x of omega equals the sampled excess of capital omega, replacing omega by omega over t0. And so that would also mean that omega equals omega times t0. And recall, so to find a time point for that correspondence, if we look at what happens at omega 0, that frequency, of course, is 2 pi over t0, which is our sample rate. That's omega 0 times t0. So that tells that frequency corresponds to discrete time frequency of 2 pi. And so we see here 2 pi is in the same location as omega 0. This equation tells us that we have the same value. And so all we have to do is line up the axes, and at 2 pi in discrete time frequency should correspond omega 0, and 4 pi, of course, would then correspond to 2 omega 0, and so forth. And so we have essentially the same picture, and only the frequency axis needs to be relabeled. And so the discrete time Fourier transform is computed directly, again, from the data that comes out of the A to D converter, the x of n, to discrete values. And it's computed directly using the discrete time frequency in radians per sample. And so, again, this is radians per second for the Fourier transform of that sampled signal. Again, that's the sample comprised of the impulses and so forth. X of omega just comes from the sample values. And so whatever the original diagram where we just had finite height sample values along the index n. And so just the first is a regular Fourier transform of the impulses. Now we've defined the discrete time Fourier transform, which gives us a spectrum that looks the same, except the frequency axis is now the discrete time frequencies. So here we'll do an example of a discrete time Fourier transform. This particular signal is a sequence of 3 ones at n equals 0, 1, and 2. It is also the impulse response of a system described by this difference equation. And it's the impulse response of a 3-point moving sum, the sum of today's stock price, yesterday, and a day before. So I'll let you work out those details, but right now all we need is the impulse response, which is 1, 1, 1. So to find the discrete time Fourier transform, plug it into the definition, and the sum values of h of n is from 0 to 2, since those are the only 3 non-zero values, and the value of h of n is 1. And so we have the summation formula. If you recall, we had the summation formula for alpha to the n, and so this is of that format when we rewrite it as e to the minus j omega to the nth power. And so we can use our summation formula. And so I get 1 in the numerator, 1 minus alpha to the n plus 1 power. That was the upper index, and 1 minus alpha in the denominator. And so this is a pretty common kind of format in many system responses. And so I'll use this to show a trick. So it's called splitting the exponent. And so what we'll do is we'll multiply up front by half that exponent. So instead of e to the minus 3 j omega, I have e to the minus 3 halves j omega. And so when I multiply the second term, I get the full e to the minus 3 j omega. When I multiply the first term, I recover the 1. So that's a very common trick. I do the same thing here, except now I'm splitting exponent of j omega, so I have j omega over 2 up front. And of course, the reason to do that is the numerator and denominator, the term in parentheses is now the term of Euler identity for sine. And so I get 2j sine. The 2j's will cancel in the numerator and denominator. Also, I get a phase term, so e to the minus 3 halves on the top minus a half on the bottom ends up with a total phase of e to the minus j omega. There is also a phase contribution I'll mention real briefly. There will be jumps in phase due to the sign. The sine function alternates from positive to negative in the numerator, and so that will introduce jumps of 180 degrees in the phase shift, which we would also see. For now, we're most interested in the magnitude response. We notice that this looks a lot like a sinc function. It looks a lot like a sine of x over x type sinc function, except in the denominator, instead of x, we have another sign. And as we saw, the discrete time Fourier transform is periodic, and so it should not be a surprise that both the numerator and the denominator are periodic functions, so the whole function will be periodic. So again, we use the summation formula in arriving at this result. One of the first things, so sine at, what is the value at 0? So we have sine of 0 over sine of 0 for omega equals 0. And so we could use L'Hopital's rule, but perhaps an easier thing to remember is that for very small angles, sine of theta is approximately theta for very small theta. And so near 0, our sine of 3 omega over 2 looks like 3 omega over 2. And the sine of omega over 2 looks like omega over 2. And then we also have the e to the j omega. Now, when we take the magnitude of this, e to the j anything has a magnitude 1, so it doesn't contribute. And so we see that the magnitude near 0 should be 3. And so our peak value of this function is 3. This is similar, to a sinc function whose value is 1 at omega equals 0, where we have 0 divided by 0. The other thing to notice is the function will go through zeros more quickly on the numerator since it's a higher frequency in the numerator. And so where the sine function in the numerator goes through 0 is where the whole argument equals pi. And so that would occur where 3 omega over 2 equals pi. So omega equals 2 pi over 3. And so at 2/3 pi omega, we see the value of the function should be 0. Finally, the highest frequency, remember the DTFT is periodic and repeats every 2 pi. And so the highest frequency at pi, it will start repeating itself. And so the function would, of course, repeat again out at 2 pi. So at the highest frequency pi, before we get into another period of the frequency response, what is the value? So we have sine of omega over 2 in the bottom, so sine of pi over 2 is 1. And in the numerator, we have a sine of 3 pi over 2, and that is also 1. And so the magnitude of the response at pi is 1. We've used the discrete time Fourier transform here to get a sense of what the frequency response of a system whose impulse response is 1, 1, 1. If you recall, if we did in continuous time, if you have a rectangular pulse, the frequency response of a rectangular pulse is also a sinc function. And so we see, unsurprisingly, that the frequency response of this rectangular pulse in discrete time has a sync-like function. The main difference being is that it's periodic because all DTFTs must be periodic. Is this a low-pass filter? Well, yes, because the highest discrete time frequency is on, off, or 1 minus 1, 1 minus 1, and that corresponds to the frequency pi. And so we can see that the largest response is at 0, or DC, and all frequencies higher than that have lower response. And so yes, this is a low-pass filter. Its DC response is 3. An interesting thing to see from the equation form, if I have a 1 volt DC, then x of n is always 1, and so I would have 1 plus 1 plus 1, and so the output would be 3. And there again, we can see that the DC gain, even from the equation above, would be 3. So a few things to see in this DTFT example. We use the impulse response to calculate the DTFT, the frequency response, and we see that the DC value corresponds to what we would expect from the difference equation, the output of a DC signal. Another thing to consider in the DTFT is that we can take the DTFT across a block diagram. So the discrete time Fourier transform of G of n is G of omega. H of n gives H of omega, and Y of n gives Y of omega. And also the property of convolution means that the convolution in time results in a multiplication of the two DTFTs. So an important interpretation of this is that we can look at these two time domain and frequency domain viewpoints as like two different languages that describe some fundamental process. So if these were circuits, the fundamental process would be electrons bouncing around, but the time domain impulse response and the frequency domain response of the system are two different languages that describe some deeper meaning or some physical system. And so typically you want to be fluent in both languages so you can choose the easiest way to solve a problem. Good question, is time or frequency the true representation? Well, in a sense, neither. That's a question for the philosophy department. Our primary interest as engineers is that can we predict the outcome? Can we predict whether the bridge will vibrate or whether the aircraft will fly properly and so forth. So this, whether or not time or frequency is the proper view is less important than we can predict the final